Hello, thank you for tuning in to this talk titled Executing Graphs with OpenCL. My name is Erik Tomusk. In this talk I will be giving you some background into why executing graphs is important, why that should happen with OpenCL. I will then talk about what graphs look like to the OpenCL API. I will show some empirical graphs that I have extracted from real-world applications, and I will finish with some conclusions. Before I get to the technical details, I need to include a little bit of background about me. I work for a company called Codeplay. We're based in Scotland, in Edinburgh, and we partner with hardware manufacturers to support open standards and APIs on their custom hardware. About me personally, I'm a software engineer. I work on the Compute Aorta team at Codeplay. Compute Aorta is our product for implementing open standards APIs like OpenCL and Vulkan. I work mostly on the OpenCL runtime side of things, and that's the perspective I'm bringing to this talk. I won't talk much more about the Compute Aorta product, but at last year's IWOCL, my colleagues Alistair and Ewan gave quite a thorough overview of this, so if that's interesting to you, I encourage you to look this video up. Also, I need to give a shout out to a number of my colleagues. For this talk, I had to look at several layers of the software stack that I'm not used to, and there were a number of people at Codeplay who were very helpful for helping me get my head around it. So with that out of the way, let's get to the technical details. This is the slide where I've gone on the internet and I found pictures, and I'm going to use those pictures to try to convince you why the topic of this talk is important. So when we're talking about OpenCL, we're often thinking about hardware accelerators. And when someone says hardware accelerator, what they're usually thinking of, or the first thing that comes to mind, is a GPU, or a graphics processing unit. And GPUs have historically been designed to be able to crunch lots and lots of numbers in parallel, because that's what you need to do to draw graphics onto a computer screen. So under the hood, and after some gross oversimplification, a GPU really is a way to do a lot of SIMD operations, so that's single instruction multiple data. And at some point, people realized that this type of computation was really useful for things other than graphics. And as a result, the OpenCL API was developed, and this allows programming GPUs to do general purpose computation. Now, something that's been happening over the past few years is that some more different types of hardware accelerators have been showing up in the industry. And I've included a few pictures of those here. So the first of these that I've included is a diagram of the wafer scale engine from Cerebras. The second diagram is the IPU from GraphCore, and the third diagram is the Grayskull chip from TensTorrent. And what these accelerators have in common is that rather than having a single render pipeline the way a GPU might have, these accelerators are composed of a large number of mostly independent computational units. And these accelerators will have some distributed memory on the chip. The individual computational units will also have some local memory, and there are some very complicated networks on chip to try to shuffle data around. So these accelerators look substantially different from what a traditional GPU looks like. And the question we're faced with is, how should one program one of these accelerators? But before we can answer that question, we need to understand why these accelerators exist. And the short answer to that is machine learning. Machine learning requires a huge amount of compute resource and a huge amount of memory. And it so happens that a lot of the tasks that machine learning needs to perform look like graphs. So here I've just drawn a simple artificial neural network with some input nodes, some hidden nodes, and some output nodes. And we know that machine learning is hugely important to the industry at the moment. And because machine learning tasks look like complicated graph executions under the hood, there are a number of hardware vendors out there that are designing these very large hardware accelerators to accelerate the types of graphs that machine learning problems want to execute. And so the question becomes, since OpenCL predates the machine learning revolution and some of these accelerator devices and the types of neural networks we're trying to execute at the moment, where does OpenCL fit in with this picture? So often it's easy to think that if there is an artificial neural network like the one that I've drawn here, and if I have access to a graph accelerator device, then I can just run this neural network on this accelerator device. But this really isn't the case. So in fact, these machine learning models, they're implemented with some sort of machine learning API, which exists on top of some machine learning compiler, which is used to convert the model to some lower level representation. And the machine learning model exists on top of some sort of machine learning library, which provides utilities and runtime support and so on. Underneath those pieces of software, there will usually be a device compiler, which is specific to the particular accelerator device, and it's used to compile code down for that device. And all of the stack needs to exist on top of some sort of device driver, which is used to access the device. And this software stack, all of it executes on top of some sort of CPU. And it's really just the device driver that does the communication with the accelerator device. So there are a number of different stacks in the industry that try to bridge this gap between a neural network that someone might be working with and the graph accelerator that someone might want to run the neural network on. And depending on who you talk to, different people will put different names onto different boxes in this diagram, and they might divide the boxes up differently. But we have this fundamental problem that there is quite a bit of distance between a machine learning model and an accelerator device. One of the software stacks that we work with at Codeplay looks a little bit like this. So the machine learning model will be implemented inside Python. And Python really just provides an interface to TensorFlow. So TensorFlow will take the machine learning model, it will convert it into some sort of graph, which is composed of TensorFlow operations. Then TensorFlow uses the SYCL backend to convert these operations into C++. And SYCL will then compile the C++ operations to some intermediate representation. And all of that information is passed down to OpenCL. And OpenCL works with the device driver to then dispatch that machine learning graph to the graph accelerator device. And that means that when we're asking questions about how we execute graphs with OpenCL, what we're really asking is, what does the OpenCL implementation see? And what does it understand about the graph, and how can it explain that to the device driver? So the execution graph comes down from the SYCL layer, and the OpenCL implementation is tightly integrated with the device driver. And this can really play out in two different ways. One option is the good option, that the machine learning model, by the time it comes down from SYCL, when OpenCL sees it, it sees something that looks like a graph. So OpenCL can see that there are different nodes and different operations. Some of these might be in parallel. The graph shows OpenCL where data must be moved to. And if OpenCL has this information available, it can work with the device driver to dispatch this graph to the accelerator device. And that way we can get good performance and efficiency. But there's another option, and this is what a lot of people are concerned about, that by the time the execution graph gets to the OpenCL layer, maybe a lot of information has actually been lost. And maybe what the OpenCL layer actually looks something like this, just a sequence of operations. And if this is what it looks like, then OpenCL no longer has access to graph information. And that means it isn't able to correctly dispatch the work to the accelerator device, and we don't get good performance. So this really is why we're concerned about what graphs look like on the OpenCL level. And so to understand that a little bit more, I'll show you a little bit about what OpenCL actually knows about when a graph is passed down to it. So OpenCL is based around the idea of executing kernels. And kernels are basically just functions. I've drawn one here. I've called it K1 for kernel 1. And the OpenCL manages data in buffers. So here I've drawn 3, buffer 1, buffer 2, and buffer 3. And OpenCL has ways of attaching buffers to kernels. And buffers might be inputs to a kernel, or they might be outputs, or a buffer might be used as an in or an out. Now the software stack I'm looking at here, it doesn't have very good ways of expressing whether a buffer is an input or an output. So I'm just going to draw these buffers without an arrow attached to the kernel because they might be used as an in or an out or both. Now, when the OpenCL sees a kernel, it also sees when kernels are enqueued for execution. And that means that a kernel has been tied to some buffers, and then it's dispatched to the device for execution. And that means that OpenCL knows that these buffers in this kernel are used together. That also means that if some of these buffers have been used before, OpenCL knows that the data comes from somewhere else. If a buffer is new, then OpenCL knows that the data hasn't come from anywhere, that the buffer is empty. And if the buffers are used later, OpenCL also knows about that. So I might dispatch a second kernel that uses the same buffer. So this takes us to a key observation that the way buffers are used inside OpenCL implies data dependencies between kernels. And this is what a graph looks like as far as the OpenCL API is concerned. So I'll say a few more things about graphs in OpenCL. OpenCL thinks about commands in terms of command queues. And that means that whoever is using the OpenCL API is submitting commands to a queue. And a command might be something like execute a kernel, or it might be something like copy some data to an accelerator device, or copy data back from an accelerator device. And command queues allow the OpenCL API user to enforce happens before type dependencies between kernels. There are two types of command queues in OpenCL. There are in-order queues, and with these, the OpenCL API is able to infer dependencies based on the order that commands get enqueued in. There are out-of-order command queues, and with these, the OpenCL implementation is not allowed to infer dependencies based on the order that the commands are enqueued in, but instead the user of the API is expected to attach events to commands and then use those events to explicitly define dependencies. Now there's this very helpful paragraph in the OpenCL specification, and it's got the sentence that says, quote, "An implementation can reorder commands even in an in-order command queue," end quote. And what this means is that if the OpenCL implementation sees that there are two kernels enqueued that don't have a data dependency on them, it means that the implementation is allowed to run those kernels at the same time or in a different order. And this means that the OpenCL implementation has latitude to schedule work to a graph accelerator device in a way that is appropriate for that device. And for the rest of this talk, I'll focus just on in-order queues because that's what the software stack that I'm looking at is using. So I've given you some background about why we care about executing graphs and what a graph looks like in OpenCL. So now I'll show you some graphs that I found in a real-world application. So what I did was I just took a very simple handwriting detection neural network and I trained it. So this was on top of TensorFlow 1.9.0, and I'm using the standard MNIST example. So if you ever go to learn to use TensorFlow, this will probably be the first or second tutorial that you do. So it's a very simple entry-level example. For this study, I simplified the neural network even further so that the graphs I get have a chance of fitting on some of these slides. And in the future, if anyone's trying to reproduce this work, I was using an earlier version of the TensorFlow Python interface. The current TensorFlow Python interface is called Keras, so I was using the interface before this. I'm using TensorFlow with the SYCL backend, and I'm using the Compute CPP SYCL implementation. I'm using SYCL with the OpenCL backend, and I'm using the Compute Aorta OpenCL implementation. And since I have access to the Compute Aorta source code, what I did was I instrumented OpenCL API calls. And that meant I was able to trace the training and inference stages of using this neural network. And then with these traces, I have some scripts that convert them into graphs. So remember I said I'm using a simplified neural network. And what I just mean is, so the standard MNIST example looks like this. There's some input pixels to the neural network, there are 2 hidden layers, and there's an output layer. And this neural net is used to detect handwritten digits ranging from 0 to 9. For this study, what I did was I removed one of the hidden layers. And that means that this is not a particularly good neural network for doing handwriting recognition, but it has all the interesting features of a neural network, which means that it's a little bit simpler to look at, and we can look at what it does to the software stack and look at some graphs and understand what's going on. So first I'll show you the execution graph of doing inference with this neural network. And inference just means that I'm showing the neural network a picture of a handwritten digit, and I'm asking the neural network what digit is in this picture. If I run this neural network and I don't show it any pictures, this is the graph that I see. So it's just doing some data setup. There are 3 kernels that are executed. Each of them has 2 buffers, and there are no dependencies between them. If I then show this neural network one picture, this is the execution graph. And if I show the neural network a second picture, this is the execution graph. So you can see a pattern developing. The execution graph for just the first iteration and the second iteration are the same. And this kind of makes sense. It's just running the same set of operations to determine what the digit is that's in the picture. If you look at this graph closely, you can see a chain of data dependencies through the graph. So you can see that a buffer comes in, and then a sequence of kernels is run on it, and those kernels use some other data buffers, and then that becomes the output. So obviously, looking at this on the OpenCL level, we don't know exactly what's going on, but given that we know that we're running inference, we can kind of guess that this is the input picture coming in that's going through a series of transformations to work out what the digit is that's written in it. We also see a few other patterns. So here, for example, there's a data buffer that's used in the first iteration and then in the second. And actually this happens also here and in a few other places. So what's noteworthy about this is that because this particular software stack doesn't make it clear whether a data buffer is being written to or read from or both, it's not clear if these buffers are being modified by these kernels. Most likely they are not being modified because this is an inference run, and most likely these buffers contain the weights that belong to the neural network. But this particular piece of information is hidden from the OpenCL layer with this particular software stack. Also, what's interesting is that there's a second set of kernels that's run in each iteration that doesn't have a data dependency between itself and most of the other kernels that's run. And I don't really know what's going on here, but I assume it's some sort of bookkeeping and data crunching that's going on. So that's what the inference graph looks like. And next off, I'll show you what the training graph looks like. So training is the process whereby you show a neural network a picture, and then you incrementally modify the weights in the neural network so that the neural network learns to recognize that picture. And I will only show you one iteration of training this neural network. And this is what it looks like. So it's quite a complicated graph. And if you look closely, you can see some of the same patterns that we saw before. You can see lots of interconnected buffers, and some buffers are used in some way, some buffers are created, some buffers are used a few times and then not used anymore. I'm not going to dig too much into this because it's quite a complicated graph. I will say as an aside though, that this is a good example for why training is quite a difficult problem and inference is, relatively speaking, a simple problem. And when hardware vendors come to design hardware, the training hardware is quite difficult to design, and the inference hardware ends up being quite a lot simpler because training is just such a more difficult problem. So remember, the question we're asking is, what do graphs look like as far as OpenCL is concerned? And what I've done is I've taken this neural network and I've plugged it into the Python interface. And what we can see is that on the OpenCL level, this is the graph that OpenCL knows about. So this really is the key takeaway from this talk. If there's one thing you remember, please remember this, that on the OpenCL level of the API stack, an execution graph is visible. And this means that it's theoretically possible for the OpenCL implementation to take this graph and dispatch it to a graph accelerator. Now, there's a few other things that are important to note. Again, like I said, what I've shown you is one iteration of training or two iterations of inference. But even this very simple handwriting detection neural network takes thousands of iterations to train. So the graph I showed you is only a very small subset of the work that would actually have to be run. As an aside, it's also worth noting that some APIs like Vulkan have an abstraction called command buffers. And these allow the API user to place a series of commands into a buffer and then dispatch that buffer several times. Whereas with OpenCL, the graphs that you saw, they have to be constructed for every iteration. So if OpenCL were to support command buffers, it would make this type of graph execution simpler. Also, remember that the MNIST example I showed you had just one layer. But in the wild, the deep neural networks that are being used today often have hundreds of layers. So again, the examples I showed you have much less work than what you would see real neural networks doing. And I've pointed this out at a few points in the talk, that this particular API stack hides some information about buffer producers and buffer consumers. And there could be a few ways to improve on this. One option would be to explicitly declare buffers as read-only and write-only. It's also possible to place buffers into the constant address space in OpenCL, or to use out-of-order command queues, and that way the OpenCL implementation is allowed to make more liberal assumptions about how it can reorder accesses to a buffer. And finally, sometimes accelerator devices have specific features that OpenCL doesn't initially understand, so it's possible to roll device-specific OpenCL extensions so that OpenCL can understand more about what it's meant to do in a certain situation on a certain device. So to conclude, I hope I've been able to convince you that OpenCL can be used to represent a machine learning type execution graph to a graph accelerator. However, it is very important to remember that just using OpenCL itself does not guarantee that an accelerator device will see a graph, because there are many ways to do this wrong. It's possible to get this wrong in the API stack. So the API stack I showed you is quite good at converting the execution graph into something that OpenCL understands. But it's also possible to have an API stack that doesn't do this well and that hides graph information from OpenCL. And also it's possible to get this wrong in the OpenCL implementation. So you could have a graph accelerator and you could have a graph that's visible to OpenCL, but OpenCL just doesn't do the correct thing, dispatching the graph to the device. And it's important to remember that more often than not, users don't actually write OpenCL code. They will often use a much higher level API that will have some OpenCL backend. So it's really the API developer's responsibility to ensure that the APIs a user is using are able to communicate the graph that the user wants to execute down to the OpenCL level. And then it's the OpenCL implementer's responsibility to ensure that the graph that OpenCL knows about gets communicated correctly to the graph accelerator. So this takes me to the end of the talk. If you're watching this as part of IWOCL 2021, then I will be hanging out in the Slack channel for the next few days. So if you have any questions, please ask them there. Otherwise, you're also welcome to send me an email at this address. And if this type of work looks interesting to you, then we're hiring at Codeplay and we're always looking for great people to join us. So thank you for listening and please enjoy the rest of the workshop.